So let's go through in a little bit more detail how we can actually calculate the initial and final values. So step one is to just draw the circuit that we have with the switches in the appropriate position. So if we want the initial values, then we want the switches before they change. And for final values, we want the switches afterwards. Then we go through and we replace inductors and capacitors with their steady state DC equivalent. So to remind ourselves, basically for inductors, we get a short circuit. So inductors become a short circuit. DC will just flow straight through inductors. Short circuit, let me just clean up my writing there. Short circuit, and capacitors will become open circuits. DC cannot flow through capacitors. And then we solve the circuit. So we use the analysis methods that we've already learned about in this class. So let's have a look at an example. This one is problem 7.35 from the textbook. It asks us to solve for the current that is flowing in this inductor as a function of time. And we have a switch here which will close at t equals 0. So to analyze this, let's have a look first at the initial current. So what I'm going to do is draw what the circuit looks like for times less than 0, so before the switch closes. So before the switch closes, this is what my circuit looks like. I have 250 volt source. I have a 50 kilo ohm resistor. I have the inductor, but the inductor will behave just like a short circuit, so no need to draw it as an inductor. I'm only interested in the steady state DC behavior. The 50 kilo ohm resistor is in parallel with a 1 milliamp source. So let's analyze it. I need to solve for the current that's flowing here. Look, a few strategies that you could pursue here, but let's just pick, say, do this as a nodal analysis. So if I define a reference node and a node voltage V1 here, then I can solve for V1, and then finding the current is going to be fairly straightforward. I'm going to write this as I0 here, the current. This is the initial current that I'm trying to solve for. So using Kirchhoff's current law at that node V1, the current I0 that leaves in the leftward branch is the following. So it's V1 minus 250 divided by 50,000. The current in the downward branch is V1 divided 50,000. And then I have 1 milliamp of current entering. So I can multiply everything out by 50,000. So 50,000 times 0.001 is just 50. So I will wind up with the following: V1 minus 250 plus V1 minus 50 is equal to 0. Bringing together all of these terms, that's 2V1 is equal to 300, so V1 is equal to 150 volts. So it's actually a lower voltage than what is coming from this power supply here, so the current is going to flow in the opposite direction. And that's basically because we have this current source here that's kind of forcing that current to flow in that direction. So therefore our current I0, just using Ohm's law here, so the voltage across that resistor is V1 minus 250. The resistance is 50k, so we can substitute in our numbers, 50,000. And so we will wind up with, so that's 150 minus 250 divide 50,000 will give me negative 2 milliamps as the initial current. Next step is to find the final current. So for the final current, if I look at the circuit, once the switch closes, the reference node, or if I call this my reference node, then it actually extends all the way along here. So basically it has the effect of kind of completely isolating the voltage source on the left-hand side, right? This voltage source out here will be completely isolated from the circuit. It will have no impact at all. And so I can redraw the circuit in a fairly simple way. For the purposes of this video, I'm just going to copy this down so you can see it on my screen at the same time. So I'm just going to put that down here. So the final current, the circuit after the switch closes is going to look like this. So there will be basically short through to ground through that switch. There will be the inductor. I'm going to draw the inductor here because I also want to find the time constant. So I'll just draw it as an inductor for now. So that's 100 millihenries. There will be 50 kilo ohms, and there will be 1 milliamp, and that is it for my circuit. So I'll just get rid of this one, make some space. That's my final circuit. The current that I'm interested in here, IF, is this one. And so just to DC, that inductor is a short. So the inductor is a short to DC, which means that all of the current that comes from this source is going to flow through the path of least resistance, which is the short circuit straight through the inductor. None of the current will go through the resistor. It's like a completely one-sided current divider where this part here will win all of the current. So kind of reading straight off the circuit, that final current is going to be just 1 milliamp, and it's in the same direction, so it's positive. So with that, I am pretty much there as far as writing out the final value for my circuit. The only other thing that I need is the time constant. So the time constant. Now, the time constant, we need to know the resistance in the circuit. And it's a bit like finding a Thevenin equivalent resistance, right? If we have independent sources, we can turn them off in order to get the time constant. So turn off all independent sources. So if I turn off that current source, then it becomes just an open circuit, and so I just have the resistance by itself. That's 50 kilo ohms. And so my time constant is simply L divided by R. So I can sub in my values. L was 0.1 henries. Resistance is 50,000. So you always have to do these calculations in SI base units, right? So that's 0.1 divide 50,000 is 0.0000002. So that one, perhaps a little bit, be a little bit careful with the number of zeros. Basically, that would be 2 microseconds. Sometimes it is convenient to calculate what is 1 divided by the time constant. So 1 divided by the time constant is going to be just 500,000. And the reason why that is convenient is that that's what we put in our exponential. So therefore, we can write out the final value for our transient. So our general solution is IF plus I naught minus IF times e to the minus t over tau. So we can just substitute in the numbers that we have. So I final is 1 milliamp. I initial was -2. So negative 0.002, I should say, then minus IF is that, and then e to the negative, and it will be just 500,000 times t. And we can clean up these numbers here. So I have 0.001 plus, I should write minus here. So minus 0.003 e to the negative 500,000 t. And that's it. That's the final solution for the transient behavior of this circuit.